Hey, fellow mathers, we've got exciting news for you.
Yep, registration for the free Math is Figureoutable Challenge is now open.
Get ready for a fast-paced learning experience where we'll outline some traps of algorithms, demonstrate how to identify if they're trapping your students, and offer guidance on how you can adapt your math instruction.
There's going to be special guests, new free downloads, prizes, and most importantly, high-energy, engaging sessions.
Join us for 3 one-hour sessions from January 29th through the 31st at 7 p.m. Central Time. Register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the episode. Hey, fellow mathers, welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
We know that algorithms are amazing historic achievements, but they are not good teaching tools because mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
We invite you to join us to make math more figure-outable. Dun-dun-dun.
Hey there.
Hey, Kim.
How's it going?
Well, we get to play with some math today.
No more poking?
No more poking. Last week we did all the poking. Today,
Okay, all right.
Let's do
some fun.
Let's get some mathing down. So one of the things that I am noticing and have been kind of fussing with for a while, especially as I travel around, I'll do some mathing with people. And then depending on people's experiences, they will often say, oh, yeah, we do that. And I'm super curious then because I'm like, you do what? What do you do? Oh, we do number talks. And that's not what we do, really. And so at least often it's not what they are referring to. So then I drill down a little bit and I'm like, what do you mean that you do that? And they're like, well, we let kids solve the problem any way they do. We do these talks once a week. It's really fun. And I'm like, what do you do the rest of your math time? Well, we do traditional, like maybe they don't say traditional, but we teach what we're supposed to teach. So we do this kind of fun thing where we kind of have kids do this, I don't know, creative, whatever. And we've taken care of that. And then we get down to the business of actually teaching what we're supposed to teach. Mm-hmm. I hear that a lot. Mm-hmm. So today we thought we would give a really good example of what we mean that mathing, and when students are mathing, that it's more than them getting answers. That if we do really good problem strings, we get a different result, a different set of mental actions happening in students than if we are either having them solve the problem with an algorithm, some memorized step-by-step procedure, or even if we're having them do some kind of a number talk or what I would call a problem talk, that there's sort of different things happening. And we thought we'd illustrate that today in maybe a different way than we ever have. For sure that we have never done this on the podcast. So y'all hold on tight because here we go. So very first, I'm going to suggest a math problem. So 18 times 25. Mm-hmm. And listeners, if you get a chance, maybe pause the podcast and at least estimate, like get some sense of the relationships. You're welcome to solve the problem any way you want, but we really want you to kind of have some sense of the magnitude of the relationships that are involved here, the answer, before we kind of superimpose someone else's strategy. So thinking. All right. So Kim, the first thing I'm going to do is just kind of talk a little bit about what could happen if a student was solving this problem, 18 times 25, with the traditional algorithm. By the way, when I was in Croatia, the Croatian teachers taught me the Croatian traditional multiplication algorithm.
Oh, fun. Which
is so not exactly equivalent to ours. It was really, it was quite fun. But similar actions happen in that you're still using the distributive property. You're still treating numbers as if they're digits. And so let's go ahead and run through what our traditional algorithm looks like. So I've written 18, the multiplication symbol, 25, draw on the line. If I am an algorithm kid, I could at this point say the first thing I'm supposed to do is do 5 times 8. And so I think I need 5 8s. So I could go 8, 16, 24, and I could find those 5 8s by skip counting, adding up 5 8s. Now I could think about 8 5s and maybe skip count by 5s, but either way, that's additive reasoning. And I could do all of the single digit multiplication facts using additive reasoning and get the correct answer. So I could be looking like I'm a multiplicative reasoner because I'm getting the answer correct. But in reality, all of the single digit facts could have been happening by me skip counting. So that's one thing. Another thing that's happening in that algorithm is I'm not thinking about 18 25s or 25 18s. I'm thinking about 5 eighths, and I write down the 0, and then I put up the 4, and then I'm thinking about 5 times 1, and then I'm adding 4, and then I'm writing that down below, and then I'm putting the magic 0 or the turtle lays an egg or whatever it is that kind of keeps track of that place value place. By the way, in Croatia, they just move the numbers over. They don't even write a 0. And they're like, well, of course there's a 0. We just move it over. We don't write a 0. Anyway, then I keep going. So then I could do all of the addition by using counting strategies or single digit additive reasoning. So I get an answer. I could have been using counting strategies and single digit multiplicative additive reasoning by skip counting. At best in that algorithm, I could be using single digit multiplicative reasoning. That is the most sophisticated reasoning. And you're like, yeah, it's a good thing, Pam, because kids can't do anything these days. And so we've got to give them the most simple, easiest thing to do. But then all we get are answers and kids using less sophisticated reasoning, which means they haven't built their brains to do something more sophisticated.
Yeah. So, and you started us today
yeah.
by saying, check out the problem and at least like estimate what it might be before we start talking about the answer.
Yeah.
If kids are drilled into algorithms, I highly doubt that that's their first move, is to think about what might be. You know, these are often the kids who round afterwards or fill in the estimation line afterwards.
That's what I did. Yeah, when we had the whole reasonable estimation approximation unit, I was like, this is dumb. Just solve the problem and then round it off.
Yep.
Like if you're going to end up doing the work anyway to do all those steps, why bother estimating to begin with?
Yep.
Yeah. Anyway, when you're in that fake math land,
Pamela,
I know
we got to work on that.
Fake math
or not? Land? I could totally be the fake only one who feels the way I feel.
Yeah, who knows? We'll keep talking about it. So, one thing that we wanted to suggest today is I could solve that problem, get answers, but not really building my brain. That's one outcome for this problem. Another outcome from this problem is I could say, hey, class, let's do a number talk today, or I call it a problem talk. The problem today is 18 times 25. What do you got? Kim, I'm going to call on you. 18 times 25. Go.
Okay. I'm going to say that I don't want to talk about 25s and
you have so many choices. You don't even know what to choose.
I'm seriously struggling. I'm going to say I'm going to quadruple the 25.
Okay.
And I'm going to do a fourth of 18, which
you can't do a fourth of 18. Just kidding.
So half is 9, half again is 4.5. So I'm going to quadruple quarter and get 4.5 times 100. So that is 450.
I'm super curious, when you did 4.5 times 100, did you think to yourself 45, 400?
I did. Yeah, I did.
Yeah. So Kim and I often will scale by 10 and then 10 again to get times 100. Yeah, nice. Okay, that's a great strategy. And I might model that on the board by writing the 18 times 25 and then saying we're going to quadruple. So a scaling arrow times 4 and then a scaling arrow divided by 4, ending up with an equivalent problem. 4.5 times 100 is 450. Cool. I could have also modeled that on the board if I wanted to with an open array, an 18 by 25. And I could have cut that 18 in half and then cut that in half again to make a really skinny rectangle and moved all those pieces over and ended up with that's not tall 4.5 by 100.
And that would have been my same strategy represented on two different models.
Yep. Nice. Cool. Then I might call in another kid and I might say, hey, how are you thinking about 18 times 25? And at that point, and I'll just throw out a different strategy, I might think about 25 18s. And I might think, well, 25 reminds me of 25% or 0.25. And that reminds me of 1/4. So I'm going to solve not the equivalent problem, but a similar problem or a related problem. I'm going to solve 1/4 of 18. It kind of sounds a little bit like what you did in the quarter part. A quarter of 18. Half of 18 is 9, half of 9 is 4.5. But now I've got a quarter of 18 is 4.5. That's like 0.25 times 18 is 4.5. And then I might scale that times 100. And now I have 25 times 18 is 450. So I'm using similar relationships, but I'm really thinking about it a little bit differently. So I was thinking about fractions, not like, you were quadrupling and quartering, and I was really
Mhm.
thinking about a quarter of 18 and then scaling that up.
Mhm.
We also might have a kid say, do you mind just giving us an
Sure.
over strategy real quick?
Yeah, so I might say I need 18 25s, but I know 20 25s is 500, and I'm going to subtract two 25s, which is 50. So 500 subtract 50 is 450.
Nice. So I might then put all those on the board, choosing hopefully a model that would help us kind of compare those a little bit. And then I might say, okay, that's great. Problem talk done. What do
Mhm.
we get out of a problem talk, Kim?
I get to share my strategy.
Okay. Yeah. Anything else?
I might see my strategy represented on the board because you represented my thinking.
Would you agree that I get agency? I get to solve the problem however I want. I have choice.
Uh-huh. Yep.
Rather than the thinking that there's only one and only one
Mhm.
right way to do it. I get some
Yep.
agency. Like you said, I
Mhm.
might get mine on the board.
Mhm.
I would suggest get exposed to the idea that there's more than one way to solve a problem. I don't know that most students seeing Kim's strategy once or my strategy once or whoever's strategy once, I don't know that that's enough for most students. I'm going to
Mhm.
suggest it's not enough for most students to actually own that strategy.
Mhm.
So I see a lot of people doing number talks where the outcome feels like it should be we just got really flexible,
Mhm.
but in reality, most kids didn't learn anything from anybody else. They just kind of once they shared theirs, then they were
Mhm.
off on their own doing whatever because they'd shared and they were done.
Mhm.
And if we really take the time to share everyone's strategy, there's only so many, and
Mhm.
now we're going to have duplicates on the board, and we're just going to kind of call into question the efficacy of that. Like, what do we gain? Do we gain enough? Do we gain enough? Yeah, go ahead.
And there are some really nice things about a problem talk
Keep going.
for the purpose of what we're talking about. Kids learning more strategies is what you're saying that's not enough for.
Yeah, so
Because I can
depends on your
see,
purpose.
yeah, I can see that the way I thought about it was different than you thought about it. Or if the teacher's doing a nice facilitation, I might hear how yours is related to mine, but slightly different.
Mm-hmm.
I might see if you put my strategy on two different models, I might see how it looks on two different models.
Mm-hmm. Mm-hmm.
Um, so there are some things that can be.
Let me throw out one more. If we have already developed the strategies that you and I just did, I think we just did 3 of the major 5
Mhm,
multiplication strategies. If we've already developed those strategies, now we get a chance to compare. And I
mhm,
left that out of the conversation, but I could have
yep,
said, hey, for these numbers, this problem, which of
mhm,
those strategies do you want your brain to be inclined toward
mhm,
next time?
mhm,
That sends a real growth mindset message. You have access to this, send your brain the message, ooh, I want my brain to do that next time.
uh-huh,
But it also gives us the opportunity to talk about the relationships and for
mhm,
students to go, for those numbers, I really like this one. Now, for these numbers, a lot of strategies are actually pretty nice. And so we really kind of care less which strategy wins the comparison.
mhm,
It's more the conversation. We want kids
mhm.
talking about the relationships that are in the different strategies because we gain from that. So definitely some nice things that we can gain from that. Let's do something. Let's do a problem string,
Okay.
and then listeners, we're going to talk about what do we gain from that experience.
Mhm.
All right, here we go. Kim, first problem: 10 times 25,
250.
250, and I am going to represent this in a ratio table. So I'm going to say we're talking about 25. So I've just written down a ratio table 1 to 25. And then you said 10 times 25. So now I've got 10 to 250.
Did
So
you make
what
yours horizontal or vertical?
I want to guess.
I bet yours is horizontal.
Oh, it's vertical.
Oh, that's so funny because I'm normally vertical and I did mine horizontally.
Oh, that's funny. Yeah, that's funny. Okay, cool. So I've got 1 to 25 and 10 to 250. Next question. What about 2 times 25?
50.
That's not hard. So now I've got 2 to 50. Next question. What about 20 25s?
I'm going to scale from the 2 times 10. And so it's 500.
So 50 times 10, and that gets you the 500. And I'm going to then suggest, or I'm going to ask, we have the 10 there.
Mhm.
Did anyone think about doubling from the 10 to get to the 20? I'll trail off. I won't try to say too much in hopes that someone goes, oh, yeah, I did. And then I want to compare those a little bit. I want to say,
Yep.
hey, what do you guys think? If you're walking down the street and you had to find 20 times 25, would you prefer to find 10 25s and double, or would you prefer to find two 25s and scale times 10? Have the conversation. In an older grade, we might actually write that down with expressions. We might write down something like 10 times 25 times 2, or 2 times 25 times 10. And note the commutative property and kind of some associative property stuff going on. And we could kind of talk about properties. Anyway, so Kim, can you think of an advantage to either one of those, 10 times 25 and then double, or 2 times 25 and then scale times 10?
I think doubling and then scaling tends to be particularly nice when you have funky numbers because then you're just scaling at the end. You're not like doubling larger numbers. Like
Mm.
sometimes if you have like 384 doubled is maybe not as easy for some people if they can double it when it's just a little bit smaller of a number.
So, like, if you had to have 384 times 20,
Hmm.
you could do 384 times 10, but then you have a big number you have to double. But you could double that smaller number, and then you just scale times 10, bam, is
Hmm.
pretty readily done.
Hmm.
Okay, cool. Next problem. How about if I were to ask you 18 times 25?
That is 450.
And I know we just did that problem, but maybe you can kind of forget it. What is there anything that a kid might use that we already had in this string to help them think about that?
Yeah, they probably do the 25s minus the two 25s.
Bam. So this string is kind of pointing towards that over strategy that you used when we did
Hmm.
the number talk, the problem talk. But we could bring that out. Okay, so we've got the 20, we've got the 2. We could also then say which of those two strategies to find the 20 25s would help you with this 18 25s. I don't know if that question makes sense. In other words, if I'm looking for 18 25s, does it make sense for me to find 10 25s, double to get 20 25s? Then I still have to find two 25s to subtract from the 20
Hmm.
25s?
Hmm.
Or would it make more sense to find the two 25s to get the 20 25s? Because then I just already have the 2 and the 20 to subtract to get the 18
You mean
25s.
outside of the problem string? Or because we already have the 10.
Yes.
Okay, so on my
Yes.
own, if I had to solve 18 times 25,
Yeah.
it probably wouldn't go 10 of them, 20 of them, back 2 of them because I'd have to find the 2. But it's really nice to have found the 2, found the 20 because that's all I need.
And you have all you need. Yeah. And the
Yep.
2 helped you get the 20. It's kind
Yep.
of nice. All right. Nice.
Yeah.
Great. Next question. 3 25s.
75.
The next question. 30 25s
750.
times 10. And the next question. 27 25s.
Mm-hmm. 675.
And how'd you get that?
30 25s minus 3 25s.
Which was the corresponding 750 minus
75.
75. And that got you the 675. Cool.
Mm-hmm.
And tell me about that. If you were walking down the street and somebody
Mm-hmm.
said
Yeah.
27 times anything,
I could think about what it's near, a nice friendly number that it's near. So 30. And so I could really find 3 of them, 30 of them, subtract.
bam. That seems like a kind of helpful strategy that we could kind of have kids start to develop.
Mm-hmm. And in this particular string, you've got 2 instances of that where it could be a conversation with the 2 and the 20 and the 18. And then you lob it out again immediately after to see if anyone's picking up what you're having a conversation about just
Yeah.
previously. Mm-hmm.
Yeah. And it's a multiple access task because if kids aren't generalizing yet, they're just kind of
Mm-hmm.
really focused on the problems, then they're allowed to do that. But we're also challenging all students to really like start to see those patterns and think about the fact that,
Mm-hmm.
for example, if I was trying to find 44 times something, I
Mm-hmm.
might find 4 times that thing
Mm-hmm.
to then scale it to get 40 times that thing and then add the 4 and
Mm-hmm.
bam, like I've already got kind of what I need.
We have talked about this before on some episode, and maybe more than one, that problem strings are an art, that there's a nudge, that they're going somewhere, there's a purpose. And I know that some teachers right now are thinking about a problem string and they're going, wait, but like I let my kids solve it however I want or however they want. And
Hmm.
even though there might be a goal of the string, they can still solve it however they want. And that's true. They, on their paper, at their desk, whatever, can solve however they want. But the conversation is not about a bunch of different strategies. As you go through the problem string, there is a focus, and the direction that the teacher's headed, the conversation's supporting that goal. It's
Hmm.
like in a problem talk, there's different conversations about different kinds of strategies, and in a problem string, the conversation's more narrowed.
Especially if you're trying to develop a strategy. If
Mhm.
you're trying to develop a model, the conversation can be
Yeah,
you can ask for lots of different strategies because you're trying to really get good at the model
right.
or a big idea. But if
Mhm.
in this problem string, we're really trying to focus on a strategy
Yeah.
or building some relationships that kids can use, then we're gonna focus the conversation, not demand what kids do on their paper, but focus the
Mhm.
conversation. Yeah.
What's really nice about a problem string too is that you're giving kids the opportunity to do lots of different things. So in this particular strategy, or in this particular string, that was the work that was on a ratio table had a strategy of over that you were going for, but
Hmm.
there was still some really nice conversation, or in my head there was a conversation about doubling, about scaling, about times 10, about quarters. Like all of those things were in my head as I was doing this work. And because there are multiple problems in a problem string, I'm doing more math than in a problem talk where you ask me how I solved that one problem that one way. I might be a Kim who's sitting on the carpet, and as the kids are talking, I'm staring at the numbers and I'm thinking about lots of other ways I could solve it, but I might not be. I might be a kid who solved it one time and then that was the whole thing.
Hmm.
So you get more math, more done in the same amount of time.
Yeah, all the mathing that you just mentioned that we get out of that problem string experience, compare that to the mathing or not that we got from a kid solving the problem using the algorithm. Even
Mhm.
if we had them solve 15 or 20 problems using the algorithm, the kinds of mathing that would happen as they're doing that versus the kind of mathing that's happening as we're taking kids through a problem string like this. They're getting lots of answers in both cases, but the amount of mathing that's happening is significantly different.
Yeah.
Look what we get from mathing.
Yeah, and because kids need more and more and more experiences to really make sense of what's happening around them, the more that we can do with them that's meaningful, the better for sure.
And giving them those meaningful experiences with constant feedback. Like in a
Mhm.
problem string, they're getting if I'm doing 1 through 29 odd, lots of problems, maybe I'm getting correct answer feedback, but that's it. In a
Mhm.
problem string, I'm getting lots of feedback on my thinking over and over and over again. A high dose of patterning. All right, cool. Y'all, thanks for joining us. Thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com and keep spreading the word that math is figure outable. Thank you for listening and making math more figure outable.
To learn even more about making math figure outable and how to teach it that way, join us for a free challenge starting January 29th, running through the 31st.
All you need to do is sign up and show up. Register at mathisfigureoutable.com/challenge.
That's mathisfigureoutable.com/challenge. Looking forward to seeing you there.
And making math more figure outable.